আমি এবার এটা দেখে নি
তাহলে
আবার আবার করছি
লাইভ
শুধু অফিস বেরোটা দেখছি
ঠিক আছে স্টার্ট কর আরে
হ্যাঁ,
তুই ওদের কাউকে না দিয়ে বলতে যে আমাকে আমি তো খুলে বসে আছি
পাঠিয়েছি
লিংকটা
ওই গ্রুপটাতে ওই লিঙ্কটা
তুই স্টার্ট
আমি
কর আমি
এবার এটা
দেখছি আমার
দেখে নি
সাথে খোলা আছে
hello, can
তুই স্টার্ট
anybody
কর
confirm am I audible in the YouTube channel?
চল চলছে তো
আমি
নাকি
আবার করছি শুধু
হ্যাঁ বল এবার কথা বল
am I audible?
একদম একদম পারফেক্ট
Cool.
পারফেক্ট পারফেক্ট পারফেক্ট
Please share this link everywhere.
ওকে পাঠিয়ে দিলাম তাহলে
হুম
হ্যাঁ বল এবার কথা বল একদম একদম পারফেক্ট পারফেক্ট পারফেক্ট
So we're starting right now, and good evening and welcome to day one of our webinar, Work in Optics. As we all have been working and studying from home, we did not get a chance to organize seminar, talks, outreaches, etc. like previous years. And thus, with the support of our esteemed faculty at the Department of Applied Optics and Photonics, the SPY OSA and OSI Students Chapter at Calcutta University has decided to organize a 2-day long event on various topics. All questions can be asked on the WhatsApp group or as comment on the YouTube stream as well. We hope you enjoy the webinar series. For the first talk today, we have Professor Siddharth Sin Majumdar, guest faculty at the Department of Applied Optics and Photonics, University of Calcutta. Sir will speak on the topic Introduction of Robotics and the Role of Optical Devices, Sensors, and Systems. Over to you, sir.
Uh, Good evening. Thanks to all students and scholars. Am I audible?
Yes, sir.
I convey my thanks to all the students of the student chapters and SPO and other forums for organizing this webinar. Uh, and in fact, today my topic, as you have already mentioned, introduction to robotics and role of optics, devices and sensors and systems. Now, basically, why did I choose this particular topic? I Can you see the slide?
No, sir,
Hello,
sir. You need to present the screen.
hello. Are you seeing my screen?
No, sir.
Hello, Arman,
No, sir.
Anupam.
No, sir. We cannot see your screen, sir. You need to
Visible,
present now.
visible.
Not yet, sir.
You cannot see. You cannot see.
No, sir.
Hello. Then
No,
why
sir. We
should I
cannot see.
share?
No, we cannot see your
Right. Wait.
presentation, sir.
Right. Wait. 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 I don't know why you cannot see. Wait. 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 Yeah. Screen sharing and errors occur. At 1 minute.
আরে তুই
1 minute.
ওদের
1
কাউকে
minute.
না দিয়ে বলতে যে আমাকে আমার
Good evening and welcome to day one of our webinar, Work in Optics. As we all have been working and studying from home, we did not get a chance to organize seminar, talks, outreaches, etc. like previous years. And thus, with the support of our esteemed faculty at the Department of Applied Optics and Photonics, the SPY OSA and OSI Students Chapter at Calcutta University has decided to organize a 2-day long event on various topics. All questions can be asked on the WhatsApp group or as comment on the YouTube stream as well. We hope you enjoy.
Can you see now? Is it visible?
So 1 second,
Hello,
sir.
Arman.
Yes, it is visible, sir.
Visible. Okay. Fine.
Yes, sir.
Fine. So basically, good evening once again, and thanks to all the students and scholars of AOP and the student chapters for organizing AOP. Already it is some 15, 20 minutes late. Okay, better late than never. And basically today my topic is, as you already told, that it is introduction to robotics and role of optical devices, sensors and systems. Now, why did I choose this particular robotics? Now, basically, although it's the emerging subject, everywhere it is being discussed, whenever any forums I've seen, but especially in this pandemic situation throughout the globe, throughout the world, in our country even. So everybody wants the minimum human intervention and more robotical activities in every spheres of life. Forget about the medicals and all, in anywhere, maybe in our day-to-day life. The minimum human intervention now is sought by all the government level, official level, worldwide level, and a lot of monies and funding and being done for this activity. And now, secondly, while discussing this robotics activity, in background mode, a lot of optical devices, sensors, and systems are working since the inception of robotics. But these are not being discussed in such forums. So this is the opportunity to discuss because now, if truly speaking, everything is converging towards optics, and photonics is the talk of the day, should be the call of the day. Anyway, now in my first slide, you are seeing a robotic arm, a finger pointing to something. Basically, a robot usually whatever foresee, whatever you visualize, a robot means a human-like kind doing some activity is coming and moving like that. But it is nothing but all constitution of these links and joints and these actuators, all these things. So at the fingertip, it is pointing towards some defined, some destination, some exact location. For that, all these links and joints have to be activated, and for that background, some other activities are there. So it's consisting of so many areas that I'll cover. Anyway, I'll wherever is possible, I'll try to highlight our optical devices, sensor systems. But there are n number of optical activities that will not be possible. Wherever it is possible, I'll try to escalate. Now, this is now I'll cover here today in brief robotics basics, selecting mechanical frame of references. Now, this mechanical frame of reference is one area where we need to concentrate for doing any robotics activity, any robotical activity. Without that, you cannot achieve a single step. Now, selecting the motors, the controllers, and actuators, because these actuators will control the mechanical frame of reference which is selected. Number two, now selecting the sensors, which will do the environment sensing, and accordingly the actuators and motors of this will work, then frame of reference will work, and ultimately robot will work. Now, role of optical devices, as I said, is very important in imaging, not only imaging, this should be the convergence of all activities, that should be the photonics. Okay. Now, optical devices, sensors including vision systems, this is very important, the vision system. The active fingertip, at the fingertip, basically, at the fingertip, basically, you can visualize a vision system is that is visualizing, and that is being analyzed, and the robotic activity is going on. Now, basically, now selecting microcontroller now naturally.
কালকে তো খুব সুন্দর sound
Hello, hello. The mic is on. Please put up your mic. Some disturbance is coming. Hello. Now selecting microcontrollers and interfacing. Naturally, at the heart of the robot, the heart of human. This microcontroller and processor must be there. Now, step-by-step introduction of a robot, because not only our student faculty, so many other faculty. Hello, hello, hello.
One second, AJ sir, I would like to request you to. Sir, I would like to request you to turn up your mic, AJ sir.
Some disturbance is coming, some noise is coming. Now, the step-by-step integration of the robot. Now, if someone wants to have your own robot, maybe some of students or scholars in his or her activity want to have some robotic kind of activity, they can just start the activity after this session, what I believe. Now, continuing on robot, obviously with the AI, but here today I am not concerning with AI, because that itself is a big topic. It will cover whole one day. That may be taken up separately. Now, basically, basic component of robot. Now, you see, as I discussed the robotic arm, basically you can see a shoulder kind of thing. Now, this is an elbow, this is the arm, this is the fingertip. And these are all, what all of these? These are all frame of references, robotic activity, that kinematics, what we say. Now, this has been given by the motors and actuators and the joints, etc. Now, at the right side, you see what is symbolized is the same thing. Now, basically, I see a picture here. Now, what human can sense that robot cannot, or rather, what robot is smarter than humans? This will be a question. It's a continuous cycle of questions. Now, human having intelligence, and you can say it seems like ice cream. It seems the color like a ash, maybe a chocolate, maybe deep gray chocolate, maybe some other is having some flavor I do not know. Maybe by skill I can see, oh, this not the ice cold. I can estimate all these things, but a robot can precisely measure. It can just little bit task tirelessly, not like a human. After some time I'll say, I don't know what is this. It may be asking. It has capabilities it can do. It is ruggedized, it can be micro or mini and gigantic robot. It is ruggedized. So if we merge these two activities, right side and left side, ultimately I have to put more and more humanoids into robotics because it can be intelligent enough to human and more than human. It can analyze whatever is the color, the flavor, the ingredients, etc. etc. Now, so using a camera, a robot can capture millions of pictures. But what are those pictures? How we can know? It should have some background knowledge. It should have some background programming. So a distance sensor robot can see my distance, but robot can not unless it knows the what micro inch I should or should not go. Now, basically, a robot can differentiate between the objects placed before on the table. Like, what are those objects? For example, this is the integration of robotics and humanoids. More and more humanoids go into robotics, becomes a real robotics in real life. Okay. Now, already since I'm going to be a bit fast because already 15-20 minutes is we have spent before that. Now, basic areas of the robotics, the mechanical engineering, as we started with the kinematics, the manipulator, the robot design the first concern. Then the electrical engineering concerned with primarily the robot actuators are to the drive, the motors, and then the microcontrollers, etc. Then optics and photonics engineering concerned with optical devices, optoelectronics, and sensors. Instrumentation, obviously the control and all the control is there. The computer science, the background algorithm is totally depend on the computer science, that this sensor, the sensing, then after is visualizing, then analyzing, all these things will be done, and accordingly the intelligence, the continuously developing intelligence will work in the background. Now, without telling history of robotics, this introduction of to robotics will not be really fruitful. But I will not cover 100 pages. It's only one page, because if we really want to cover it, is 100 page of history. Now, Karl Pekov in 1920, he wrote one play, Rossum Universal Robot, in Czech, that robot means a tireless worker, continuous work, and ultimately they revolt against the creators. We have seen so many movies like Star Wars series, like Terminator, etc. These are all basically imagination of robotics. Now this imagination has really turned into robotics. Now rover has been sent to Mars, etc., etc. The imagination start in 1920 itself. Now, basically, I will tell only the landmark in the one page. Like 1970 is the landmark of Luna 17 lands on the moon, carrying the remote control robot Luna Code 1. 75 is the Viking 1 and 2, is the articulated robot arm, as I shown in my very first slide. Now, 1976 is the film Star Wars R2D2, the second generation robotics started. The 1978, the 1979, the two very landmarks in milestones in the robotics, the Puma and Scala, the programmable universal machine for assembly by Unimation. And the SCARA is a selective compliant articulated robot for assembly, is a selective compliant, selective movement, selective
Excuse me,
axis
sir.
selection, the
Um,
movement of
s-
the robot. So
Hello,
introduced
sir.
by Japan and US by ADAPT technology. In
Excuse me, sir.
2004, the Mars rover sprint lands on Mars. In 2010, NASA and General Motors they joined hand, and Robonaut 2 is astronaut in Robot Astronaut in 2010. There are
Excuse me, sir.
landmarks in between.
Hello,
So many activities I'm saying the landmark. Now
sir. Can
2019,
you hear me?
last but not the least, the
Hello.
Chandrayaan 2 was a six-wheel robotic vehicle named as Program. All of us know about that. So up to say this 50 years, brief I have covered in one page. I am not going much uh, beyond that. Now I right now told the frame of reference. What is that? That can be several. Is all a mechanical subject mainly. There are wall frame of reference. There are joint frame of reference. There are tool frame of reference. Now, you see the pictures here? The wall frame of reference. There are movement in specific direction. Say one axis is fixed, other axis is moving in rotation x y z. Now there are joint frame of reference. When a joint movement is there, is rotational and torque and this all these activities end effector. Then there is a tool frame of reference, like the movement in all axes simultaneously. So these tools are available for designing the kinematics of the robotics. So readily available, or some can also develop with the available system. Now, what I right now told, this is a practical example of a SCARA, the selective compliance, the articulated robotic arm. So this fixed in one base, and then the other joints are moving on legs. So this is the actual implementation of SCADA. Why I'm showing? Because unless we have some basic knowledge of what is there inside, how the robotic structure is defined, how the robotic structure is formed. So only should not visualize is a microcontroller processor. I put some sensor, I put some wheels, the robot will work. It's not like that. So basically, this is a SCARA, is assembly line robotics. This is actual implementation of the commercial implementation, the SCARA robot. Now, now, now coming to a little bit of optics. Now, this assessment of kinematics is so precise, in so higher resolution that can be achieved by optical methods only. Now, optical fiber is a methodology where the macroband sensing of this movement of the joints and links can be done with the optical fiber. Now, basically here what is done from the base of the robot, maybe robot arm, a fiber goes to the tip, maybe up to finger point, and it comes back. Then while light comes back, it's there's a macroband losses due to bending and stretching, and that can be sensed. And similarly, a three-dimensional sensing can be done with this macroband sensing. I'm saying the pictures here. Now, so see the picture. This is a robot arm, say this is a base, this is a robot fingertip. It goes on the bending, directional bending, all these things. It light comes back like that. This is a 3D picture where I can say three directional all these macro. This is the optical process, the precision and the resolution that can never be attained by any other methods, any other devices. Now, basically, there's optical moire. This is another thing. So, basically, in soft robotics, what is that? Basically, a very, very tiny kind of robot is what the very silky kind of say head and tail is there with the robotic tiny micro robotics, and that can use for medical and other different purposes. And basically, what is the moire? Basically, to transparent and opaque frames, they are overlap and they are lit, and there is a slightly special difference between them, or maybe angular difference. The fringes change accordingly. The change of the fringes, the actual orientation, actual stretch, actual strain, actual bending can so precisely define, and the micro stickering is done on these robotics on the head and tails, and is self-lited, and it gives the continuous information of bending in the micro level and down to that level. So this is the citation how the delta theta and this are changing. This is a optical method. Now there are other methods like this ligament stains and all these things. These are being by very high resolution digital cameras. Now, this moves, we can calculate the 3D coordinates of the contrast markers put on the robotic parts and bodies and arms, maybe, and the system precision, and it's set in different angle, and depending on the case-to-case basis and various angles, the accuracy is defined. So here, you see, at 60 degree, it is giving the highest accuracy with this particular orientation. Now 3D coordinates can be measured, and the translation down to the level of 0.008 mm is the suggestion from paper I have given, and a degree down to the level of 0.02 degree it can be measured. And these are all optical methods where this kinematics, where this movement of the microbends can be, firstly it can be calibrated, secondly it can be implemented in actual robotics, and this should be the top of the day. Now I have covered up to the this robotic this kinematics, this mechanical part of selecting. Then what is an actuator? Basically, actuator which transfers some kind of energy into some motion. Now, basically, a DC motor is a type of actuator. We have seen how the robotic arms, robotic legs, robotic parts are moving. Some motors must be there. Now, basically, two basic concerns is there. First, the rotational speed, what I need for that. And first, for selecting actuator, I have to consider 2 points. Now, point number one is the torque, the force that I need, or the rotational speed I need. Now, there are several types of motors, DC motors. Just for example, I am saying for basic knowledge, those who wants to proceed, do something with the robotics activity, they can go ahead. They're already available. Now, DC motor is basically is a gearbox that can be geared down, gear up for making different torque as per the requirement. RC servo motor is a DC motor based with a potentiometer with measuring the angle, etc. Now, stepper motor for giving step, the angular step, maybe 1 degree, 0.1 degree, 2 degree, like it's a stepper motor. Now the linear actuator, basically it is a lead screw connected to the DC motor. As a solenoid, basically is nothing but moving, pushing up and down, pushing left and right, depending on the actuation of the solenoid by current. Basically, now the thumb rule actuator for robots. Is the actuator being supposed to move a wheeled robot? Now, robot must be put on a wheel. Robot must be put on a track. Now, these have to assess what for what I'm selecting. Just like I should not go and do the actual practice sequence with the DC motors and all. Now, basically, once again, the DC motor as a brush and a commutator and a tacho generator. What happens here? The actual movement and feedbacks being controlled with the potentiometer. Sliding potentiometer is a resistive in part. What happens over a time slot? It cannot retain the accuracy, cannot retain the resolution, and naturally noise are generated. So what is the way out? Once again, the optics. A rotary disc consisting of a transparent and opaque space and a LED and a detector. If it is fitted instead of using any resistive component at all, it will never be differentiated, never be drifted. And this is being used heavily in robotics for getting the actual information of robotics motions and angular velocity, all these things. Optical gyroscope is another way out, another novel way, the real actual way, which is being sent to Mars even, which is gone to Chandrayaan, which is gone to any other spacecraft, etc., etc. Now, the disadvantage with the mechanical gyroscope is that they contain moving parts, their friction in terms of output drift over time. But a fiber optic gyro, basically a fiber optic coil, there is no interference, and there is a big coil, and in two opposite direction, laser light is being sent, and by this time it may move a angle theta, and the outcoming that the difference of phase is modulated into the translated into the intensity, and that gives the precise of angular velocity. No question of drifting, no question of going bad, no question of over time this spoiling all these things. There are ring laser gyro also. The only difference is in ring laser gyro there are optical mirrors. This is the only difference. Otherwise, the policy is the same. So these are the gyro. These are all optical and all optics. These are being heavily used in robotics. And now I've covered the basically robotic kinematics, which is the robotic frame of reference. Then I gone to the optical devices for that. Then the robotic the actuators, how the actuators to be selected. Then the different optical methods for measuring or the actuation, all these things. Now selecting track versus wheel. How the robot will move? It has to have some wheels, right? Or program. It has some is a 6-wheel robot. 6-wheel was there, which is going to Chandrayaan 2. Now, whether it's a wheel or whether it's a track. Now, power efficiency is the question. Now, for a wheel robot, the drive geometry is defined by how each one is steered. Now, individually, one wheel can be steered, 2 wheels can be steered, or 4 wheels can be steered, maybe back and forth. But the track, it moves as a whole, like a pattern tag. You must have seen the robotic symbols like pattern tags elsewhere. And here also, the encoder is a good way out to get the actual movement, actual rotation, all these things. Is optical system only. Now, now I have to go to the heart of the robotics, which is the microcontroller or microprocessor. Now it has to have some microprocessor, microcontroller. Now basically what is that? Microcontroller having some pin in and pin out, where some digital analog signals may come in, may go out. Now microcontroller, these signals, the pins are we make high and low, depending upon the sensing environment, depending upon my commands, all these things, and it works. There are various variations of microcontrollers, like initially the primitive microcontrollers, the simple 8-bit microcontroller, that also was used initially for robotics maybe 50 years back in 1970s, 80s. Now 2000 onwards, the Arduino, the students community are mostly using. It's a very cheap for the robotic application. I'm not saying the high-end application, but a basic robotic application, say driving a car, maybe sensing some information or giving some feedback. This Arduino is a very good. Then the Raspberry Pi is the talk of the day. Basically, here only the processor overhead is increasing from this old microcontroller to new microcontroller to the Raspberry Pi. This is a ARM processor. What is ARM processor? Basically, it's a rich kind of processor. Basically, what it does in any processor, what I do, we execute the instructions over some machine cycles and instruction cycles. Now, here what is done? In each machine cycle, one instruction, like the multiple instructions in one instruction cycle can be executed instead of a single signal. This is the main advantage in robotic computation. Now, huge data, the big data, it needs the ARM kind of processor only. Now, a typical representative technology using Raspberry Pi, there is a system on chip. Now, basically, with a 1.5 gigahertz 64-bit quad, what is quad? Quad processor is a 4 processor in a single chip. So basically, this where ARM processor with the Raspberry Pi having some 1 million byte of shared L2 cache, because instead of memory they put cache, a more electrically a memory or storage, which is very costly and keeps the recently used data. So these are the facilities with the Raspberry Pi. For the so advanced work can be done in the Raspberry Pi. So all students community, science community, scientist community, they all mostly using Raspberry Pi. Obviously, there can be high-end users also. So in that case, still high-end you can go for processor, but Raspberry Pi is the talk of the day. Now, now basically, what are the bottlenecks if you go on using this type of processor, increasing single core, dual core, multi core? Now, basically, uh, the Raspberry Pi is a credit card size. It come in a pocket. Is a computer that plugs into the regular monitor, TV, etc., etc. Wherever I can go, I can take it. Now, let me introduce a different versions of Raspberry Pi, because someone wants to what they will come across the nomenclature. The Raspberry Pi 1, the 0, Raspberry Pi, then Raspberry Pi 2, Raspberry Pi 3 is all basically with the basic facilities, number of ports, maybe number of pinout. Say with Raspberry Pi 3 is Wi-Fi and Bluetooth connectivity. Raspberry Pi 2 there is no Wi-Fi. So Raspberry Pi 2 there's having a Ethernet connectivity, so cable connectivity. Now software platform is the Raspbian, is a community, is a symbol for Raspbian community. The Raspbian OS is there. Now third-party OS like Linux and Windows that can be interfaced. Now these are the org I was given, www.raspberry.pi.org. You can go and you can free downloadable. Now Raspbian Pi Foundation recommends Python for this Raspberry Pi. Is a microcode that can be easily learned. So many Python tutorials are there available. Is free. Now, the basically other languages like C, C++, Java can be interfaced. These are the main facilities for various calls. Now, essential, the minimum bill of material. I should have a Raspberry Pi board. I should have an operating system with SD card. It will come if I purchase a Raspberry Pi. It will come with the SD card. It's like a small memory card you use in a mobile. Now USB keyboard and display, maybe HDMI, maybe normal display, maybe a TV or a power supply. Now other highly sized USB mouse for internet connectivity, LAN cable that does not come usually with the Raspberry Pi, etc., etc. Now, what are the features of Python? Why do you go for it? First, it is free, it's open source, it's portable. Now, this Python, what we program, we can convert, you can transport one-to-one to Windows, the Mac OS, Linux, etc. Now, it's extensible, like I already told, that it can be extended, it can be interpreted C, C++, and other languages with Python code. Now, it's very endless library is there. You can go and see, it's all free. So, last standard library, in fact, it can be interfaced with MySQL DB. So, a MySQL DB can be interfaced with Raspberry Pi, and that can work fine. These are the facilities. Why do you go for this Raspberry Pi and go to Python? Now, in the synopsis, the central is the Raspberry Pi with several ports, the VGA port, the USB port, other LAN port, etc., etc. Then the SD card. Then integrating it comes a Raspberry Pi. Now, as I just discussed, so the use a Raspberry Pi model with 4 core, where this speed, that speed, that speed. Ultimately, what's coming the way? So in 1980, it started with 286, then 386, then 46, then Pentium, then P2, then P4. Then after 2010, the Power 6. Then ultimately the cores are increasing, the overheads are increasing, the pins are increasing. So subsequently, the bottlenecks are coming. So now a many core is needed. Now basically, the interconnect bottles, the number of multi-core CPUs are coming, multi-core interconnections are coming, multi-core multi-caches are coming, memories are coming. So there's a lot of pins and a lot of connections, a lot of jittering, a lot of skewing, a lot of noises, a lot of hits are coming up. So ultimately, banding is also a question. So ultimately, the way, what is the way? Way is the silicon photonics, is all optics. Now, this is the talk of the day for the all this processor and all that is being implemented in so many places in the worldwide in the labs. The silicon photonics, the processor for the robotics activities. Now, basically, I'll just there are eminent speakers, those who will cover this silicon photonics a lot. I'm just in one page showing is waveguide kind of thing, and there is a ring modulator, ring resonator, and there is a say external laser source for pumping, and there is a single mode fiber, and there is a off chip, can be say maybe a board to board, maybe a chip to chip connectivity is attained. Now, nowadays it's not at least possible in a complete chip, maybe chip A, chip B, chip C, like that is intermediate connected with a single node fiber. So this is the basic concept that now I believe some of our speakers will be covering this area in deep only for this conceptual. I'm telling what is that. So ideally we have to shifting. We are shifting here also on the what we say. You can say this Raspberry Pi. You can say this PowerShell. This is ultimately the photonics should be the talk of the day, and photonic computation should be the talk of the day, even in robotics and so many labs throughout the world it is there. In fact, in 2015, researchers in US Berkeley, they made a photonic processor with the robotics activity. It gives 50 Gbps bandwidth, and likely in 2019-20, commercially they have targeted for market need. So basically, this is a manufacturing unit of this photonic processor. This is a symbol of this photonic processor. Just for the information sake, I'm covering this here. Now, the processor chapter is over. Now, controlling the robot. Now, I have to control the robot, right? Now, robot can be controlled by RF control. It can be a Ethernet, can be guided, can be unguided, can be Bluetooth, can be Wi-Fi, can be GPS by SIM over cellular, or can be autonomous. Now, autonomous also depends on the complexity of the situation. Now, it can be pre-programmed with no feedback from the environment. Is a dedicated activity of the robot. It can be limited sensor feedback, and finally it can be complex sensor feedback. It can be offline sensor, it can be online sensor, it can be sensor activity continuously changing and gaining knowledge and accordingly giving the feedback. Now these basically these are the type of autonomous type of connectivity. Now I will just cover one optical control of the robotics, that is called a Li-Fi. Now Li-Fi is a talk of the day, all of you must be knowing. Now basically it conforms to IEEE 802.115.c, is a protocol standard for international IEEE. Here what are in Wi-Fi basically is visible light communication. Now is a robot has to work in a dome, in an area, in a, maybe in a particular zone. So basically now is a simple LEDs that communicate based on my message, based on my signals, and that is being received by a detector, and that is analyzed and activity is done. Here you see the patterns of ones and zeros, and the bits are going through a series of the LEDs, and there is being received at that end. Now, basically, is a prototype model, a demo model, which a voice control robotic activity by Li-Fi. Here, the voice is synthesized by a PC, the program. There's the ARM processor, as I told, maybe a Raspbian processor, and that and the Li-Fi that the transmitted processor coming out based on the this by this voice and my command, and that is being received by the TX, the RX, and once again there is a processor, it digitizes, and it drives to the motors, that actuators, that robotic arm and robotic hand, that drives the DC motors, as I told sometimes back. So basically, this is a the light control activity for robotic control. Now we have up to the control part we have covered. Now we have to choose a sensor. Now there are various sensors, as many of you may be knowing, a lot of sensors. There are ultrasonic rangefinders. There are fixed term robots. It sends the ultrasonic wave and comes back, and the time is calculated. An infrared sensor sending the infrared sense, and then sensing by detector. Now doing the activity. Now there are certain gas sensors. Now there are GPS sensor. A lot of sensors are there. Are n number of sensors. Some I am mostly we are using, or people, students are using for their robotic activity. That I'm saying. GPS sensor for positioning, etc. Now there are optical gyro. Already I told. Now basically now I'll tell a little bit on the optical sensor, like a robot vision sensor, basically, and a robot vision sensor, the fiber optic sensor, a robot then is straps of fiber owned on robotic arm robotic and a light is modulated by that. Then for the soft robotics mainly the tiny robotics, the embedded optical sensor, this is embedded maybe within a leg, within a hand, with the robotic parts, and maybe human body even, and that can sense externally. Optical encoder already I have discussed. Then infrared sensor, then FBG fiber backdating. The FBG sensor is a very renowned sensor that can sense the any space variation down to the any macro level very precisely. Now, a vision sensor basically is a camera. More number of cameras is mounted, maybe single or more cameras mounted, and the special purpose lighting and softwares are used built in, and with other electronics. And this can be separately purchased. This can be integrated with my Raspberry Pi, with my other processors. But it depends on the requirement. I can use it. Now, fiber optic sensor is a fiber optics are owned on this cable in box. There's a camera. There's a and sensor, and depending on the surrounding it responses the fiber, the light is modulated, basically embedded as right now told is robotic arm. The sensor can be embedded in it, and is a fiber optic sensor. Now FBGs, I told the variation of the shifting of the wavelength, the delta shift of the wavelength is down to the wavelength level, sub wavelength level can be measured, the stress, strain, all activities. They're all optical sensors is being used and heavily used in robotics activity. Now, they basically just for the fun, I say just I'm showing a robot, but till now I was concerned with all these technicalities of the robots. Now, these are the robot moving on the wheels and tracks with a lot of sensors, a lot of actuators, a lot of vision system, etc., etc. Now, then then what a computer vision do for robotics. Now, basically for accurate object position, you can see a vision sensor. Now, basically is the end effector, is the actuator in the robot arm, is the target for accurate positioning, the keeping the relative position movement, the visualization, performing the exact measurement, the object recognition, and registration. These are the jobs done by a robotic vision. Now, basically, I once again go to the optical areas where the robot, the vision is and depending on the requirement, it can be edge sensing, depending on the contour sensing, it may be a fine grain sensing. So it all depends on the how the first level sensing is done. Basically, what is the image? Image is nothing but the light source emits of energy. The wavelength and the intensity subset is detected over a time period, and the sensor what is that is quantizes, and this is the energy according to spatial position. This is nothing but the image. Now, according to the architecture that is analyzed, these are the analysis we are showing here, and based on that, the actual scenario is reconstructed. Just have shown a picture how the robot is visualizing the chess player playing and how he is analyzing and then giving the checkmate, etc. Now, basically, this is the area of robot vision. Now, vision sensor. There are a lot of vision sensor. They are just few. I'm covering the optical areas mostly. The single perspective camera, multiple perspective cameras, laser scanner, omnidirectional camera, structured light sensor. Now, what is a single perspective camera? Basically, it is here what is done. So in a single line, a single camera or multi-camera is placed, and it is taken. The shots are taken, and then it is moved to other direction. Then shots are taken. But a multi-perspective simultaneously in several angles, and multi-cameras or single cameras placed and shots are taken. This technology is being used for the perspective cameras. Now, these are the views I can say. This is a visual odometry, is a contour is being constructed. This is a single perspective camera, the ray optics I have shown. This is the image plane, this is the object, and this is the multi-perspective vision is the constructing, and this is the actual robot moving with the vision camera and analyzing and all this thing in a single, a small tiny trawler, and that's moving for the activity. And this is the live example. And this is nothing but the COVID. In COVID, they are using in so many countries this vision system for analyzing the viral activity, analyzing that the virus and all. A continuous analysis going on. This is a live example that I have taken from some citation. Right now, there is 3D laser cutting. The basically is a non-contact, non-destructive technology. and digitally captures the shape of the physical objects with a line of laser light. And basically, is object scanning, laser scanning is also you can call it the LiDAR, the direction and ranging. And basically it combines control steering of laser beams with the laser range finder. Now, every direction you can take the measure, you can scan rapidly, very fast, and capture the surface shapes and objectives. These are the basically examples of live working of these LiDARs. You can say the 3D laser scanning. This is a moving, a robot moving with the 3D laser, etc. and all. They're all live examples. Now there is a LiDAR in robotics, as I rightly told. Now there's a robotic is moving on wheels and with all activities and actuators and the pneumatics and the other motors and etc. Then and the cameras and a LiDAR continuously emits lasering and it gets very quickly. It does the usually very high sampling rate. It does an individual emitters and receiver it samples and basically basically the high precision here records in optics, and basically LiDAR system uses the rotating mirrors instead of using so many channels, so many lasers. It uses maybe a single laser or one or two laser with a rotating mirrors to enable channels to sweep around the environment in 60 degrees. The typical LiDAR acquisition data, and then is analytics that for example is a live case. Now, then is omnidirectional camera. Basically, in all directions, 360 degree, or maybe at minimum level in a circle, it can acquire the data and images. Omnidirectional camera. These are regularly being used in robotics application. In a LiDAR, actually they use in basically a simple robotic vehicle, a manless vehicle, say a driverless car. They use LiDAR. They continuously goes on the roads and all. They take up the pictures, the dividers, the light, etc., etc. They simulate immediately. They can know the shapes, etc., etc. These are omnidirectional camera. These are heavily used in robotics in 360 angle view, which can be done. Now this is a structured light sensor. What is that? Basically, is a versatile method. Is a projection system. The patterns consisting of many steps in some or some arbitrary fringes. Basically, it looks like the shape is deformed. Is a projector. Is a camera, and from the deformation, it calculates back the actual shape. So these are a live example of the structured light sensor. Is a robot with moving in a wheel. When a gas pipe is drilled, or it goes a pipe is drilled in the ocean, say a robot with a wheel and all with a structured light sensor sense, it continuously goes up and down, goes below the river, goes below the this mines and all, and it continuously takes the shapes and all and gives the feedback. This is a live example of the structured light sensor. Now, I hope by up to this point we have covered the major areas of robotics, like we have started with the kinematics, the fixing of the robotic, these basic frames, the frame of references. Then we came to the motors and actuators to move that frame of references in actual scenario. Then came the controlling that there are several controlling, in fact, on optical, Li-Fi controlling I have cited here. Now, basically, then we came for the microcontroller and microprocessors. Now, basically, it's all culminating in, as I told, the photonic computation. Ultimately, it is going on in so many labs throughout the globe, throughout the world. The robotics with photonic computation. It's commercially, it is coming in the market maybe shortly, 2020 or 21. Then I have gone to the vision sensor, like up to the structured light sensor, starting from the LiDAR, then the cameras, multi-perspective, single perspective, up to this. I'm going a bit fast already, some 15-20 minutes we have lost. Now, basically, at the end of this my presentation, now basically is a picture of robot farmer. Is all I discussed that all are present over here. If you mind it, we see is all CPUs, maybe number of CPUs and number of maybe Raspberry Pi and number of the frame of references, arms and legs, and cameras, various type of, and there are several other sensors. Now it moves in the paddy field and it knows what the seeds already have been cropped or yet to be cropped, yet to be applied. Like that, it does what it's happening, is working. The real life, this robotics. Now this is a remote operations being going on. A lot of new, as why I am showing, because I a lot of the kinematics I have discussed, a lot of this structure, all this area, but this is nothing but all these structures, as you see in the actual implementation, the operation is going on. Now there's a microbots. That's for mentioning. I'm saying is very tiny silky. It can in a human body it can move, and an electromagnetic field from outside it controls this motion, and the feedback is often continuous. These are all called microbots. Just for knowledge, I'm saying. Now the goal is a robot must be acting like a people or more than a people. Now, who will give the inputs? The sensor will give the input. It depends on the how what type of the sensing the sensor is going on. Is it complex or is it dedicated like that? Now the fundamental challenge is the environment is continuously changing. Accordingly, the knowledge of the robot has to change. So there, here comes the artificial intelligence that I am not covering today. That itself is a big topic. It takes one day to cover the AI itself. That we can take up later on. So it's a challenge for continuous changing scenario, continuous changing the real world, and the physical robot is sensing and is controlling, and then once again sensing, it is changing, keep on changing. So this is the really challenge. The unless AI is integrated, it can be a fully robotics. That I want to say. Now, basically, at last, as I right now told, AI should be there. Otherwise, robotics should not be completed. I can do a robot. I can make a driverless vehicle. I can make a robot moving here and there with and doing some medical operation. But ultimately, the AI must be there and learning must be in background. The AI and the machine learning is a very big topic that can be covered in a whole day. Like basically, the robotics is a part of that. Is integrated with the machine learning. It learning over time, over surroundings and changing, and then the intelligence is going and continuously going, and that is keep working. So basically, the goal of the robotics is having artificial intelligence, means creating computing system that have the ability to perform tasks like humans or even better than humans. Basically, ultimately, I'm coming to my end slide. Now, there should be some first number one, some idea of kinematics. Number one. Second is a little bit knowledge of motors and actuators. Number three, optical methods, devices, and controllers. This is a very important point for today's is call of the day. Now, available sensors. I should know as I discuss some of the sensors. People should know what are the all sensors available so that I can select. Now, vision devices, cameras, the step 5, the step 6, a microcontroller meeting your requirements. It can be a simple 8-bit microcontroller, it can be Raspberry Pi, it can be a higher version of that, it may be a power series. Now, a startup knowledge of programming in microcode. And last but not the least, some imagination. Now, because in 1920, that the Czech playwright wrote a play drama that came into reality. That not only imagination. Now, the rover is landing on moon. So this is it comes from the imagination. So imagination then go for. So unless you do some imagination, unless you visualize what you are going to do, what you want, then only you can go to 1, 2, 3, 4, 5, 6, and 7. Now this my ending slide. Now thanks for your patient hearing. Thank you all. I hope already have taken nearly an hour or 50 minutes. After me, some eminent speakers like Dr. Bhattacharya and Professor Ajay Ghosh or Ajay the Beloved, they are waiting. So either you can take the questions, you can send pass on the letter on at the end of the session, you can answer, or if time permits, you can do right now whatever you like. Now I hand over it to Anupam once again to keep on. Thank you all.
Thank you, sir. Thank you for your valuable knowledge. I for the question answer round. So anyone who are eager to ask any questions can ask us via the YouTube
আমি
live stream.
শুনতে পাচ্ছি না
Sir, am I audible? Hello.
না একটু মানে আর একটু জোর হলে ভালো হতো কালকে জয়দীপ যেমন করলো খুব ভালো হচ্ছিল
Sir, am I audible? Hello.
না খুব ভালো হচ্ছে না
স্যার আপনি হেডফোন লাগান
আরে আমার তো তো ডেস্কটপ তো এখানে হেডফোন কোথায় লাগাবো তাই জানি না
ওই অডিও পোর্টে লাগিয়ে
ওইখানটা হেডফোন লাগানোর জায়গা আছে না
কেন এসেছিস
So I think now we are open for the question answer round.
আমার কথা শুনতে পাচ্ছিস কি
হ্যাঁ হ্যাঁ
Yes, sir.
আচ্ছা আচ্ছা ঠিক আছে তাহলে চলে যাবে
So everyone who want to ask questions can ask us via the live stream comment. or the WhatsApp webinar group?
We are open for the question and answer round. আমার কথা শুনতে পাচ্ছিস কি? হ্যাঁ হ্যাঁ।
So I am seeing our our Professor Ajay Ghosh and Professor Bharishiria, they are waiting. You can keep on with the presentation. You can take the session.
নো নো
হ্যাঁ
আমার বেশিক্ষণ লাগবে না, এটা চলতে পারে।
Okay, okay. ঠিক আছে।
ঠিক
Sir, Isam sir, can you please switch on your video? Everyone is like eager to see you.
Right, okay.
ওরে সব এখানে ঢুকলে তো চেঁচামেচি করলে মুশকিল।
Yes.
Yes, sir. Sir, we are waiting for some of the questions. If there are no questions, then we will move to the next speaker. That is KB sir. But we will wait for like a particular time. Let's see. Um, Sir, we have a question from Buddhadev Basak. He has mentioned that from how far can we control these types of robots?
Sorry.
From how far can we control these types of robots?
Controlling. Basically, because as I told, it can be Wi-Fi based controlling, maybe a RF controlling, maybe a cable controlling, maybe Ethernet cable controlling, LAN cable. It all depends on my, because the controlling is what I want. If I want it should not proceed beyond 1 microinch. That should be the control. Now Wi-Fi is a process I told you. That can be very precisely in wavelength. I can do the control in the past.
Thank you, sir. So, maybe we can wait a few more minutes, I guess.
ভালো আছো?
হ্যাঁ
আচ্ছা,
তুই কেমন আছিস?
এই তো লকডাউনে লক আছে।
আরে অনুপম, কজন আছে আমাদের, শুনছে কজন?
40.
40।
Yes, sir.
ইউটিউবে আছে নাকি?
Yes, sir. Sir, we have a question from our departmental professor, Dr. Konik Palodi. Sir, what is the role of optical techniques in machine learning?
Optical techniques in
Machine learning.
basic.
Machine learning.
Basically, today I told I told this particular word, this ML, machine learning and AI. So basically, this one I'm visualizing and vision, maybe a camera. I'm grabbing say some image. I have to then immediately, not only if I take thousands of or billions of pixels of noise, I have to do background analytics. Then and ultimately, what all is there in the database, it may not confirm. I may have to develop based on the vision, based on images, based on the topology. So this is a vast subject right now. All this topology and all these things I'm not covering. Basically, learning is a continuous process. An optical a sensor, a big sensor is a sensing. Now, and after the sensing, it is analyzing. It is analyzing. It may be developing a new algorithm, or maybe present algorithm. It ultimately takes action. It's like that.
Thank you, sir. We have one more question. Uh, is there any work in India for sensor level like DC motor with fiber or silicon photonics?
Is there any?
Is there any work in India for sensor level like DC motor with fiber or silicon photonics?
Fiber cellular photonics all works are going on the globe, and I can, if you can remember, some 1 year back, one of our eminent professor came from Bangladesh, all the way from US, for giving the presentation. And here, if you go and some of the factories, some of the not exactly in the factory production output is there. In the labs and all, you will find the silicon photonic activity, and it is keeping trying to keeping pace with the world. It's not like in emergency. It's trying to keep pace now. It's not in very, I should say, in India right now.
Thank you, sir. So we have no more questions. So due to time concern, we'll move to our next speaker. That is
We have
Dr.
one more
Ganesh
question in
Sir.
YouTube. That is how
Okay,
VR
yeah,
and
yeah, yeah.
XR can be implemented in robotics. Is there any application yet?
What is that, Anupam?
Um, Sir, how VR and XR can be implemented in robotics? Is there any application yet?
How?
VR and XR.
Actually, I cannot right now answer. If you take the question, I'll answer him. Okay. Right.
This is a question from Niladri Ganguly from our department. So maybe
Okay.
Niladri,
And send me. I'll answer definitely. Right.
yeah. So you can contact sir personally.
Because I am not a robot. Robot could have answered everything.
So now we'll, due to time concern, we will move to our next speaker, that is KB sir. So over to you, sir.
Thank you, Anupam.
Thank you, sir. Uh,
ওকে,
yes, sir.
শোনা যাচ্ছে?
Yes, sir. Yes, sir.
হুম? হুম?
I will just, sorry to interrupt, sir. I will just request everyone, other speakers, to please keep their mic in mute so that there is no noise. Thank you, sir.
Okay, so before I come to my topic, which is not a technical topic, but just an exposure to, I will come to it later. Before that, Jaydeep asked me to introduce the department, the genesis of the department, as also the SPI, OSA, and OSI chapters of my department. Okay, so I will start with that. This is for the, I think for the freshers who have just, who are in the first year and are still to reach our department as such. So let me start with presentation. Just a minute. Huh? Hello.
Yes, sir. Yes, sir.
Okay, so about the department, we are in the Department of Applied Optics and Photonics. Okay, I'll give you a brief genesis of the department. Way back in 1951-52, we started, it was the Department of Applied Physics. So the Department of Applied Physics started a specialization in lighting engineering. Okay? So this was basically based on illumination technology. The course was based on illumination technology. From 1952 to 61, with the specialization in applied optics and illumination technology, and the degree given was MSc in applied physics. From 62 to 69, we had this MTech in optical engineering and illumination technology. Incidentally, the Department of Applied Physics, our parent department or mother department, this was the first department to start a course in optics in India. Okay, one of the first departments. I think IIT Delhi came just after us. It was a part of the physics department in IIT Delhi with a specialization in optical engineering, optical technology. 1970 to 78, the 3 years BTech and 2 years MTech in applied optics and was initiated, and laser technology was there. 79 to 93, we had the 3 years MSc Tech in optics and optoelectronics. I am a product of this 3 years MSc Tech in optics and optoelectronics. Then from 93 to 2004, we had these 3 years BTech and 2 years MTech. Because of some complications in AICTE norms, we had to switch to this 3 years BTech and 2 years MTech format. So till 2004, in fact 2005 March, we were part of the Department of Applied Physics. In 2005, the Department of Applied Optics and Photonics was established with the existing faculty of the Optics and Optoelectronics section, as it was known then, of the Department of Applied Physics. So we belong to the Department of Applied Physics and in the Optics and Optoelectronics section. In 2005, this department was established. In 2005 to 2008, the 3 years BTech and 2 years MTech in optics and optoelectronics, which I already mentioned, we continued, but in the new department. In 2008, we had an additional course, MTech plus PhD course in astronomical instrumentation in collaboration with IIA Bangalore. So this course is being continued till now. Right now, we have another course, MTech course in biomedical instrumentation. So the Department of Applied Optics and Photonics right now conducts one BTech course in optics and optoelectronics and 3 MTech courses. One in all are 2-year 4-semester MTech courses, one in optics and optoelectronics. The second is in astronomical instrumentation, and the third is in biomedical instrumentation. So this is about the course, about the department and the course. The activities of the department, basically teaching, research, it's like any other department. And we lay a lot of stress on research, of course, students' projects, research. And also Jayako asked me to present something about our ex-students, about our alumni, immediate ex-students, okay? So let me try that. I'll give you a very brief view of our ex-students that we have. Okay, so here is a list of ex-students of the optics and optoelectronics section. You can just go through it. I'm not speaking out the names and where they are currently, but you can just go through it and you will find that from the last 10 years or so, a lot of our students are opting for postgraduate and doctoral studies abroad.
Excuse me, sir.
One of the reasons, yeah.
So we cannot see the list that you're speaking of. Can you share the screen?
You cannot see this?
No, sir. You have present now in the Google Meet, then you can share the window.
Just a minute, my computer is actually having some problems. You are able to see the earlier screen, right?
I'm sorry, sir. Can you repeat? I lost the network connection.
No, it's okay. Sir is coming back.
Okay, okay.
No. See, I'm from the this Meet page, WhatsApp, Google Meet page. I'm opening present now, right?
Yes, sir.
Yes, sir.
Then I'm selecting your entire screen.
Yeah, you can do that, or you can.
Okay.
Sure.
Or
So you can
because
just.
after that,
Yeah, so, or you can just choose a window and you can select which one do you want to. So,
I can select a window.
so whichever you find suitable in.
Just give me a minute.
Sure, sir.
Yes, sir.
Can you see the screen now? এবার দেখা যাচ্ছে স্ক্রিনটা?
হ্যাঁ স্যার দেখা যাচ্ছে।
পাওয়ার পয়েন্টে দেখা যাচ্ছে তো?
হ্যাঁ স্যার দেখা যাচ্ছে স্যার, যেটা আপনি করবেন সেটা আসবে।
Yes, sir. Yes.
Okay. Is it okay
Yes, sir.
now? Okay.
Yes.
Okay. So let me, you just go through this. I have already talked about this. Here you have the genesis of this department. Okay. And this we already talked about. Okay. Now let me just go through what I have to say. Okay. Let me go to my talk and then I'll show you that Excel list that Jadip had sent me about the whereabouts of our ex-students. Okay. Okay. Is everything fine now?
Yes, yes, it's okay.
Okay. So I wanted to talk about lasers and laser technology, the Indian connection. So what Indians have contributed to laser and laser technology, okay, especially the laser technology that we have these days. Patel. Kumar Patel, as you know, was the inventor of CO2 laser. Now, why I am speaking on these people, you will understand later. But see, all of these were educated under the Indian education system. Kumar Patel received his BE in telecommunication engineering from College of Engineering, Pune in 1958. And then he got a scholarship, went to Stanford University for his master's. He did his PhD in 1961, finished his PhD, joined Bell Labs. Okay. And then when you joined Bell Labs, Bell Lab was a place where you have to select your own area of work. Okay? So 1961 was just when the ruby laser and the helium neon laser were invented, and very little work was being done in lasers in the Bell Labs. And Kumar Patel was basically working on spectroscopy. Now, in Bell Labs, he started working in laser spectroscopy with a 3.5 micron xenon laser that he developed. So he wanted to work with laser spectroscopy, and he was developing the lasers that he required for his own work. So he developed this 3.5 micron, which is found in the IR range, xenon laser. In 1963, he applied an effect. So this was the first tunable laser system by controlling the magnetic field. And the results showed that the resolution is obtained was finer than Doppler spectroscopy, that is the laser lines split to a much finer degree than through Doppler spectroscopy. Well, however, because when you work in spectroscopy, you need a wide range of tunable lasers. So he had to wait. And in this time, this is in his own words, while you were waiting for something exciting to happen to get a tunable laser, there are other things which you should be able to do. So by this time, most people who were working on gas lasers had been, okay? Solid state lasers, ND glass, ND yard, gallium arsenide, and diode lasers had already arrived. And he says, no matter what you used, you couldn't get past that magical number of roughly 50 milliwatts. So 50 milliwatt was the limit of laser power that was available in those days. And 50 milliwatt was not sufficient for spectroscopic work. So what he did was he spent 6 months identifying the drawbacks of atomic lasers. And he realized that atomic lasers are in fact power hungry.
Excuse me, sir.
Which
Sorry to
means-
interrupt once again. Sir, can you just
Yeah.
hide the minibar that shows meet.google.com is sharing a screen? Just click on hide.
Okay. Okay now?
Yeah, thank you, sir.
Is it okay now? Okay. So then you spend 6 months identifying the drawbacks of atomic lasers. So as you know, helium neon lasers, ruby laser, this was atomic lasers. So it means that the atomic energy levels were involved in the lasing action. Okay. And he realized that in atomic lasers, a lot of energy in these systems was wasted to populate the lasing levels that are far removed from the ground state. Okay. So how about utilizing the vibrational rotational energy states of the molecules, since they are much closer to ground state, which means he worked on carbon dioxide laser. Okay, because after studying both diatomic and triatomic gases, he finally settled on CO2. And I'll show you a video later where he says that he eliminated carbon monoxide because it's a diatomic gas, and he selected carbon dioxide because it's a 4-level laser system, and 4-level laser systems are much more efficient. Okay, and the first system he built started working right away. He found from literature that the first vibrational state of nitrogen is long-lived and is close to the upper vibrational lasing state of CO2. So by 1964, Umar's CO2 laser was delivering hundreds of watts of continuous power. Okay? So this was the highest power laser at that time. And as you know, it has become the darling of the laser industry ever since. So, it's widely used in machining, in industries, and of various other applications that it has. Consequently, he went on to develop the high efficiency carbon monoxide laser. In 1967, he, along with his 2 PhD students, developed the first widely tunable infrared laser by lasing the spontaneously emitted Raman scattered light from a semiconductor subject to a magnetic field. Okay, and he continued with laser spectroscopy and detection of pollutants. Then he formed a company called Pranalytica, a manufacturer of quantum cascade lasers and gas detection equipment using laser spectroscopy. I am not going much into the details of his work. Okay, uh, I'll show you a video where Kumar Patel speaks on
Sir, we have a request from the request that there is no
Can
sound.
you see the video?
No, sir, the video can be seen, but the sound is not coming, sir.
Sound is not coming.
Yes, sir. There is no sound.
The sound is not coming.
Yes, sir.
Then there's nothing can be done.
Okay.
Okay, then I'll skip this video.
Okay.
Okay, I'll skip this video and let me tell you what he just said. He said that when he went to Bell Labs, can you hear me now? Can you hear me?
Okay.
Okay. So basically said that when he went to Bell Labs, uh, the existing lasers that were available were not sufficient for his spectroscopic work, and therefore he tried to develop his own lasers. And he actually what he did was he experimented with different combinations of gases with atomic lasers and found that there are only 2 or 3 combinations like helium neon. So you have helium and neon, which had this resonant transfer of energy from one to the other to carry out lasing. So he found that there can only be 3 or 4 maximum combination of gases, which results in these efficient lasers. So what he did was one of the things he says here, he tried to take out the helium completely from a helium neon laser and showed that it still worked. Okay, so 2 combination of gases were not required. A single gas would be able to deliver energy. I mean, not that much of energy, it's not that efficiency, but then it did laze. So with this idea, he thought of developing lasers with single gases, not with a combination of gases. Okay, and then he tried with carbon dioxide, the different vibrational levels of carbon dioxide. And then he goes on to say that in 1967, I think, he became one of the managers of the Bell Labs laser group. And he was asked to recruit proper people for the lab. And one of the dictates of the administration was that you have to hire people who are smarter than you. Okay, and he says this is a very good idea because it takes the company upwards. So you should not be afraid of hiring people who are smarter and more intelligent than you. And he goes on to say that it is my distinguished service. In my distinguished service, I had hired many people, and I am honored that 6 of them went on to win the Nobel Prize. Okay, so this was Kumar Patel. Next we come to Mani Bhomik, which most of you know. Well, his schooling was in Tomluk, Kola High School, BSc Scottish Church College, MSc Physics, Calcutta University, Rajabhadra Science College. He did his PhD at IIT Kharagpur under S.N. Bose and Paul Dirac as one of the supervisors. The topic was quantum physics and resonant electronic energy transfers, which he later applied to lasers. In 1959, he got a scholarship to University of California, Los Angeles, okay, as a postdoc. In 1961, he was a laser scientist at Quantum Electronics Division at Xerox Electro-Optical Systems in Pasadena. He taught quantum physics and astronomy at the University at California State University, Long Beach. In 1968, he joined Northrop Corporate Research Laboratory, worked on development of high-power lasers for long-distance radar as part of the Star Wars program. Now, he actually developed the highest power of carbon monoxide lasers. So we have a link between these people who I'm talking of. I'll be talking of later also. So Kumar Patel actually developed the carbon monoxide laser. He first rejected carbon monoxide as a potential candidate for lasing because of its diatomic properties. But later he himself developed the carbon monoxide laser because what he says he had nothing particular to do in that time before the advent of a high power laser. And that laser was further perfected by Mani Bhomik, who developed the highest power of carbon monoxide laser. Then he became the director of the Laser Technology Lab at the Northrop Corporate Research Laboratory. And then led his team. This Northrop Corporate Research Laboratory was based in UCLA itself. Okay. He became the director of the Laser Technology Lab and led his team to create the first excimer laser lasing at room temperature. Now, the excimer laser that he developed was a krypton fluoride laser. Excimer, as you know, it is excited timer. The important thing is that, see, fluoride lasers were discovered in Russia quite some time back. But the problem was, fluoride being a very corrosive material, after lasing, after a pulse is produced, the whole system was destroyed. Okay? The contribution of Mani Bhomik is that he incorporated an noble gas with fluoride. So it's an excimer because you know noble gases cannot form compounds. But then subjected to high energies, they actually combine with each other physically, and this was known as a dimer. Okay? So it was an excited dimer, and this is why it was called an excimer laser. And when they lased, they came back to their ground state. So he led his team to create the first excimer laser at room temperature. Well, excimer lasers, already they had excimer lasers at very nitrogen temperatures, very low temperatures, but now they could create excimer lasers at room temperature. As I said previously, I'm not going into the technicalities, the details of all this, okay? Just I'll go through the history. So, and he announced the development in 1973 in OSM Meet, Denver, Colorado, where he rose to become the director of Laser Technology Laboratory and led the team responsible for the development of the excimer laser technology, patented the first efficient excimer laser in 1976. So this is the patent of his laser. Okay. Now, he was the first to use nitrogen fluoride as a fluorine donor instead of fluorine, which corroded glass and is absorptive at KRF wavelengths, that is 249 nanometers. He obtained a power of 10 megawatts, okay, 10 megawatts, which was unthinkable in those times for 10 nanosecond pulses. As opposed to earlier versions, his laser had longer lifetime and is successfully utilized in a wide variety of applications. Well, incidentally, Mani Bhomik's laser, this excimer laser, the story goes that he, when he discovered this laser, Well, I'll come to that later because it's all these are related. You see, so Kumar Patel invented the carbon monoxide and the carbon dioxide laser. The carbon dioxide laser actually uh, was a darling of the industry. Okay, and carbon monoxide laser was there. Mani Bhomik perfected the carbon monoxide laser, and then he went on to develop the excimer laser. And then we come to this person, Dr. Rangaswamy Srinivasan of IBM Research. Well, he got his BSc in chemistry and his MS in physical chemistry from the University of Madras. PhD in physical chemistry from the University of Southern California in 1956. He got his postdoc at the University Institute of Technology and at the University of Rochester, joined IBM in 1977 as T.G. Watson Research Center, at T.G. Watson Research Center in whatever, as a photochemist. Okay. Well, his fundamental contributions on the action of ultraviolet photons from mercury resonant lamps on small molecules in solution. This was because he was basically a photochemist. So he worked on chemistry, polymers, photoresist, etc., etc. In 1980, when Mani Bhomik actually invented the excimer laser, so Bell Labs thought of having this laser, not for any particular purpose, but because it's a new laser, so the director of the group, I have this video after this, but since you cannot say, I'll skip the video, I'll just speak what he says. So the director of the group says, we spent a lot of money to get this laser, and I told Srinivasan that Srini, let us try to do something with it. Okay, not knowing what to do with it particularly, but because it's a new laser, it's a UV laser, so let us try to do something with it. So in 1980, the lab acquires an excimer laser. This was from Lambda Physics Corporation. It was too weak in energy to carry out molecular research. Okay, accidentally, Srinivasan has his nail etched with the laser. So one day while he was experimenting with the laser, what happened? The laser ran over his fingernail. And then he saw there was a neat etching, absolutely neat etching on the laser. And then he tried this with Mylar sheets. And he says that because he's a photochemist, he worked with proteins, and proteins are basically long chain molecules. Mylar sheets are also long chain molecules. So he could interpret the results, and he could know that if it does etching with Mylar sheets, then it is possibly will do etching on human tissues also. So in 1981, just before Christmas, he brought over the leftovers of his Thanksgiving turkey to the lab and made an incision with the argon fluoride laser, okay, which was then acquired by Bell Labs in 1980. And for a comparison of the etching that they achieved, a similar incision was made with a frequency doubled Nd:YAG laser at 532. So a frequency doubled Nd:YAG laser at 532 would be emitting at 532 divided by 2 nanometers, which was also in the UV. So he was comparing two UV lasers. One was a frequency doubled Nd:YAG laser, a YAG laser, and the other was the excimer laser. And he found that, see, whenever you have these etchings on, this was chicken cartilage. This was the leftover of his Thanksgiving turkey. He found that whenever you are etching with excimer laser, you have a very neat cut, because what the excimer laser does, because of its very high photon energy levels, that it immediately dissociates the molecules of the tissue, and it creates a plume which evaporates, instantly evaporates, leaving no scar tissues behind, leaving no residual damage. And see, this was the effect with the lower picture that you see. This is with the frequency double YAG laser, so you can see a lot of scar tissue around. And then you went on. Well, what he did was we used a conventional, uh, well, photo etching machine with xenon lamp. So there we had this photo etching machine with xenon lamp, because you see photolithography was always there. Okay, so for photolithography, lasers were not used in those times, but they had this xenon lamp. So what he did was he replaced the xenon lamp with the newly acquired laser. He designed the lenses. Okay, he designed anamorphic lenses, and he targeted the focused the laser light to a very fine point. Because it's a UV laser, it could be focused to a very fine point, and this was what he achieved, and it actually shook the world in that time. Okay, so this was a pattern created on a human hair. You can see this was a pattern created on a human hair, and when this is also on human hair, so you could see very neat cuts. Okay, without any uh, residual scars or residual damage, and the dimensions you can see here. Okay, these are very neat cuts. This was the first picture which actually arrived, uh, which actually was presented in his publication. And then when it was found that it could it could well, cut human tissue accurately and neatly, then Dr. Trokel, who was working as a clinical and research professor of ophthalmology at Columbia University, was invited to collaborate. Okay, and because he was an ophthalmologist, in ophthalmology, uh, lasers were already being used. In fact, before lasers, for other studies like other cures like retinal detachment, initially the first experiments were done with well, focused sunlight itself, because it was shown that highly focused sunlight could somewhat contain retinal detachment. Then came the xenon lamps. Now, when this laser arrived, Dr. Trokel was invited. He actually collaborated with Srinivasan, and they actually carried out some experiments on bovine eyes of cows, and showed that, well, with this laser, the cornea of the eye can be carved out accurately to the order of microns. Shows its application in human tissue ablation, and then Dr. Trokel and Srinivasan collaborates, and then you have this LASIK surgery. The LASIK surgery basically uses a excimer laser to shape your cornea, because as you know, the eye has the cornea in front, the eye lens, and the retina. So if you think that the eye lens contributes to 100% of the power of your eye, you're wrong, because the eye lens gives you about 30% of the power. The curvature of the cornea gives you about 70% of the power. So instead of instead of working with the eye lens, what they did was to change the power of your eye, they curved the cornea. Okay, so carving the cornea was done with excimer lasers. Okay, so the rest is history. And after 30 years in IBM, Dr. Srinivasan is the CEO of his own company, UV Tech. Well, you will not be able to hear the audio, but I think you can see it. So just have a look at Srinivasan. Sorry. This is not Srinivasan. This is Srinivasan. So he says that because I knew proteins, it was my PhD work. So when that plastic was actually etched, I knew that it could work on tissues. Okay. The next person I'm going to discuss is Kanti Jain. Kanti Jain was originally from Indore. He got his BTech from IIT Kharagpur, Masters 1975, and PhD in electrical engineering from solid state physics from University of Illinois. Uh, Postdoctoral fellow at MIT, where he conducted research in nonlinear optics. He joined IBM in 1979. Well, he's recently retired. 1980, he joined Al-Madin Research Center, develops and demonstrates the concept of excimer laser lithography. Okay. In 1981, he modifies a Permin-Elmer microalign scanning projection lithography tool, replaces the xenon mercury lamp with lambda, whatever, excimer laser, and adds a novel anamorphic. This was like Srinivasan itself. And well, then, so in 1982, he publishes this paper in IEEE Electron Device Letters. Um, High resolution optical lithography method and apparatus using excimer laser light source. Okay. 1984 acquires US patent, and jointly with Perkin-Elmer develops the first commercial excimer laser photographic tool. So the idea is, see, before this, before Kanti Jain, whatever work in photolithography we had. Now, incidentally, photolithography was a very, very important tool, is still a very, very important tool, because all your chips, all your VLSI chips that you have on your computer, okay, the microprocessors, etc., were based on photolithography. And in photolithography, what you had to do was you take the silicon chip, you cover it up with photoresist, okay, and then you expose UV light from a conventional source which was earlier used. And what the UV light did was, there was the pattern recognition process, and the pattern recognition process was somehow dissolved after development, and there from these regions diffusion had to take place. So you had multiple times you had to do this on and on. Okay, so this was an indirect method. What Kanti Jain did was he actually directly etched the wafer with his laser. There was no photoresist required. Okay, so this simplified the process of mask making. Mask making is a very, very tedious process, and mask alignment, mask making, these are very, very costly and very tedious processes. So as you see, in the 1990s, the feature size of these VLSI chips was about 0.5 microns. Okay. Presently, all these microprocessors, all these VLSI chips are not done through photolithography, but through direct lithography, direct laser lithography, okay, and direct excimer laser lithography. And it is right now below 40 nanometers. So you see this from 0.5 microns in 1990s, it's down to below 40 nanometers, 0.5 microns to 40 nanometers presently. And this is why you're getting these small size chips, because the feature size had reduced considerably. So if you look at the impact of these innovations, one after the other, Kumar Jain, Mani Bhaumik, Srinivasan, Kanti Jain, you will see a series of four Indians. All of them had their education in India. Okay, they had their basic education in India. Well, I'll come to that. So this is one of the results that they published. Okay. This was, of course, on photoresist itself. Kanti Jain is presently he's not a professor anymore. He's retired, president and founder of Anvik Corporation. So what we see is that all of these four gentlemen who had their basic education in India, then went on abroad to seek a future and pursue higher education. Well, if you think of this, then well, what had these exemplary gentlemen have in common that this revolutionized technology? Okay, what had they in common? First of all, basic Indian education, which they took seriously. Now, this word seriously is very serious. Okay, when you enter an educational institute, you have to work seriously. You have to take it seriously. Okay, so this is one thing, because right now what you are learning, it may not be apparent that it will be required in the immediate future, but when you require it, if you don't know it, then you have learned nothing. Okay, and you have to go into the scientific outlook, the research. The scientific outlook is what is very, very important, and your dedication. So, opportunity to work in the best labs. This is, of course, without these facilities, none of them would have been able to invent what they had and change the face of technology. And dedication and enjoyment in research. Now, dedication and enjoyment in research comes when you know the basics well. If you don't know the basics, then you don't enjoy research. Okay, so those of you who are freshers who will be joining the department, I would like to say that take your studies seriously. What you have in the future, nobody can tell. Okay, and of course, what I did not mention finally is some amount of luck. Okay, some amount of luck is necessary, and luck comes when you uh, persevere towards something. Okay, of course there are failures. We do not talk about failures. Well, we know that we do not talk about failures, but then luck actually comes when you stick to something, and well, if luck doesn't come in that way, you change the course, you go to something else. So this is what I wanted to communicate to you. Thank you. Do we have time?
Thank you, sir.
Okay,
Thank
I
you.
have, I think I have five minutes or so.
Okay.
So what I will do is I'll try to come back to my that Excel sheet that I was trying to show you. Well, Joydeep actually asked me to uh, show this to you, especially the freshers, to actually have a knowledge of what our students are doing now. Okay. Can you see full screen? Can you see the screen? Hello?
Yes.
Hello?
Yes, sir.
Can you see the names and all that?
Yes, sir.
Okay, okay, good. So, you see, these are some of our students, current students. Now, since the last 10 years, as I said, there is a trend of going abroad. One of the reasons being that, well, most work in photonics as such, photonics technology, uh, is being taken up abroad. Research in photonics is mostly taken up abroad. In our country, there are places, but the recruitments are few and far between. So wherever opportunities exist, you have to be ready to avail that, wherever it is. Okay? And we have seen that our students, wherever they are doing well. They're doing quite well. And one more thing is that I have observed over the years is that uh, this you should take very seriously, that whoever is whoever the teachers think is top of the class here, our experience shows that he is at the top of the class anywhere in the world. Okay, one who used to stand first in our class in BTech stood first in Max Planck Institute as well, and anywhere else in the world. Okay, so this is what I wanted to show you. So you can, this is a brief glimpse of some, I think, from the last 5 or 6 or 7 years of our students, where they are. So this is the optics students, the optics and optoelectronics students. Okay, and I have the other files. Let me see. This is biomedical instrumentation. Well, after this COVID-19, I'm hopeful that biomedical instrumentation, well, of course, biomedical instrumentation, all students, all pass outs who were eager to get jobs are in jobs, and they're doing quite well. And in fact, if you think of job prospects in India, students from biomedical instrumentation have a better chance. Okay, because well, biomedical instrumentation is everywhere. I mean, in all, I think it's a recent regulation that all hospitals, government or private, they have to have a biomedical engineer. Okay, some of our biomedical instrumentation pass outs, they also opted for research. A few have gone abroad also. So wherever you are, opportunities are there, but you have to be serious. You have to dedicate yourself. Okay, nothing. You have to remember that nothing goes to waste. Whatever you learn, you will be able to apply sometime or other. Nothing goes to waste. And finally, there's another file of IISEU. Okay. So this is the current list actually. So some of the IIA CU students are also abroad, but I think you don't have the full list. So Jaideep hurriedly actually gave me whatever he could lay his hands on. Okay, so thank you very much. It was a pleasure talking to you, and I hand over to Anupam.
Thank you, sir. That was really a very motivational speech. So, and I guess every one of us who are watching this video, all the students, it will be very helpful for them to have a better concept about the department and its future aspects. So, I will just wait for a few minutes, if sir permits, and we'll check if someone has any questions or not.
There can be no questions on this.
But still some doubt or regarding anything or okay, fine. So, okay, fine. So we'll move on to our next speaker, that is Professor Dr. Ajay Ghosh. Sir, you are muted.
So he's trying to unmute.
Yeah.
Unmute করুন স্যার। আনমিউট করুন। মিউট করা আছে। ও আপনি তো শুনতে পারেন না। না শুনতে পারেন তো?
না স্যার, স্যার শুনতে পাচ্ছি।
Anudam, can you unmute from your end?
No,
No.
actually I can't do that. It's only I can only mute during any time. Okay, sorry.
হ্যাঁ হ্যাঁ হ্যাঁ।
আনমিউট করে দিয়েছি, কিন্তু প্রেজেন্টেশনটা যাবে কি করে এখানে?
স্যার
Present now, it's okay, sir.
এইখানে প্রেজেন্টেশন
নিচে ক্লিক করুন, প্রেজেন্ট নাও বলে একটা আছে, নিচে কার্সারটা নিচে নিয়ে আসলে এখন প্রেজেন্ট নাও বলে একটা উইন্ডো খুলবে।
ও আচ্ছা, দেখছি না।
অনুপম একটু গাইড করো।
Hi, sir.
আমি একটুখানি আসছি।
Okay, sure. Thank you, sir, for this lovely talk.
আরে খুলছে না এটা,
Hey,
আরিয়ামান
ইয়েস
একটু স্যারকে হেল্প কর।
স্যার, আপনার গুগল মিটের নিচে একটা প্রেজেন্ট নাও বলে একটা অপশন থাকবে।
কি বলে?
প্রেজেন্ট নাও।
প্রেজেন্ট নাও।
হ্যাঁ, সেটা খুলছে না। এই এসছে না।
হ্যাঁ স্যার, ওকে স্যার।
হ্যাঁ, খুলেছে এবার।
স্যার
প্রেজেন্ট নাও করুন স্যার, আপনি অলরেডি
স্যার
স্টার্ট।
your entire screen করে দিন।
হ্যাঁ,
ওখানে 3টে অপশন থাকবে, তো আপনি এন্টার স্ক্রিন করে দেন।
শেয়ার ক্যান্সেল।
না স্যার।
শেয়ারটা
স্যার আরেকবার ট্রাই করুন স্যার, আই গেস হয়ে যাবে।
এটা তো হচ্ছে না।
স্যার প্রেজেন্ট না হতে স্যার আপনি your entire screen করে দিন স্যার, একটুখানি হয়তো লাগবে।
করেছি, তাতে এইটা এলো শেয়ার ক্যান্সেল।
স্যার
শেয়ারটা কি?
আরেকবার আপনি রিট্রাই করতে পারেন স্যার। হ্যাঁ স্যার এসছে।
এসছে?
এবার আপনি প্রেজেন্টেশনটা ওপেন করুন।
ইন্টেলিজেন্ট ওপেন করবো কি করে?
না স্যার, স্যার ওটা না, নিচে যেটা আছে,
স্যার নিচে স্যার
টাস্ক
আপনার
বারে যেটা আছে।
পাওয়ার পয়েন্ট যেটা আছে, ওই পাওয়ার পয়েন্টটা খুলুন।
ও আচ্ছা, খুলেছে।
হ্যাঁ স্যার, এটাকে ফুল স্ক্রিন করে দেন এন্ড স্লাইড শো করে দেন।
স্যার এখানে যেটা meet.google.com এ শেয়ারিং হয়েছে স্যার, সেটার পাশে যে হাইট অপশন আছে সেটা স্যার একটু ক্লিক করে দিন। এন্ড এখানে
হাইড
হ্যাঁ স্যার, হাইড করে দিন। আচ্ছা হ্যাঁ, পাশে আরেকটা যেটা আছে ওটা স্যার উপরে ক্রস আছে, ওটা ক্রস করে
এই তো
দিন।
স্যার দেখা যাচ্ছে।
হ্যাঁ ওকে স্যার।
এসছে।
হ্যাঁ
হ্যাঁ স্যার,
পারফেক্ট।
থ্যাংক ইউ স্যার। স্যার ইটস অল ওভার টু।
আমি কিন্তু দেখতে পাচ্ছি না, মানে আমার স্ক্রিনে এসছে, তোমাদের স্ক্রিনে এসছে।
হ্যাঁ স্যার।
video, audio সব এসছে।
ঠিক আছে, ঠিক আছে, ওকে। Well, my today's topic is after so many stories and everything, mysteries of propagation in variant beam. I was assisted by one of my scholar, Rijuparna Chakraborty, who did PhD under me long back. In fact, it all started just the beginning of this century. He came to me with these two papers and asked me to explain. The most interesting thing is that, which made me puzzled, these two words. One non-refracting, other is diffraction training. And I know in your classes, during propagation, you know, you learn Heidel's principle, which is the main for propagation, main idea behind propagation. Now, what Heidel said is a method of analysis applied to problem of wavefront, both in far-field diffraction and in near-field diffraction, also during reflection. I hope you can read it. Is it okay? It states that every point of the wavefront itself the source of spherical wavelets, and then secondary wavelets emanating from different points mutually interfere. Now, for wave propagation, obviously diffraction is essential. If you just take a wave front at a time t, each point of it produces secondary wavelets. And the wavelet propagate say after time delta t. A new wave front is formed over the tangent of all these wave fronts. And if you draw the direction of rays, it's like this. However, it has certain limitation. Not all experts agree with Huygens principle. It is an accurate microscopic representation of reality. Several scientists, including Feynman later, argued that Huygens principle actually does give the right answer, but for wrong reasons. The following facts should be noted. Those who will learn about it, I mean, you must go through this, especially this lecture, at the below of the screen. This lecture is very important and will give you the idea about how the light to wave propagates. The original analysis of Huygens include amplitudes only, but it does not include either phase or waves propagating with different speeds due to diffraction within the continuous area, and therefore does not take into account interference. But this one is more important. The Huygens analysis also does not include polarization of light, which imply a vector potential. While some waves can be described as with a scalar potential, and there is no unique and natural translation between these two. In the Huygens description, there is no explanation of why we choose only the forward going, that is retarded wave, or forward envelope of the wave, instead of backward propagating or advanced wave, that is the backward envelope. And then, in modified Huygens principle, this term, homogeneity of space will come. This is actually a fundamental to quantum field theory. Please go through it. শোনা যাচ্ছে কি?
হ্যাঁ স্যার, শোনা যাচ্ছে, আপনার আওয়াজটা ক্লিয়ার আছে। স্যার কিন্তু প্রেজেন্টেশনটা স্যার আপনি একটু
হ্যাঁ, দিচ্ছি। অ্যাকচুয়ালি আমি তোমাদের দেখতে পাচ্ছি না বলে প্রবলেমটা হচ্ছে।
তাহলে কি স্যার আমরা ভিডিও অন করে রাখবো সবাই যারা গুগল মিটে আছে, মানে আপনি স্টিল দেখতে পাবেন না।
এনিওয়ে তোমরা দেখতে পাচ্ছ তো?
হ্যাঁ স্যার।
The homogeneity of space is fundamental where the wave function of any object propagates along all unobstructed path. That is geodesic path, as I said before. When integrated along all possible paths with a phase factor proportional to action, the interference of the wave function directly predicts observable phenomena. Every point of the wave front acts as the source of secondary wavelet that spread out in a light cone with the same speed as the wave. The new wave front is found to be constructing the surface tangent to secondary wavelet. To explain the generation of diffraction-free beam with classical theory is almost impossible. Unfortunately, we normally follow classical theory to explain everything. It is possible to explain, but diffraction-free beam using classical theory almost impossible. Well, in recent years, generation of diffraction-free beams has gained tremendous importance because of the fact that under ideal conditions, they are able to propagate indefinitely without any change of the transverse intensity of light. Obviously, for this class of beams, the time average intensity profile along the propagation direction may be expressed as Ixy greater z greater than 0 equal to xyz equal to 0, which means that you see, as z increases, it will remain same. So it is not expanding, it is not diffracting. Unfortunately, these diffraction waves have infinite extent, and in reality, it is not possible to generate these waves, as it necessitates the use of a source along with the optical components having infinite extent. Nevertheless, a close approximation of this class of waves may be generated using finite aperture optical components and still maintain their profiles without significant alteration for a reasonably large range. We got over 2-3 meters, it remains almost similar structure. And we term these beams as quasi-propagation invariant beams. Now it is well known that a partial differential equation remains invariant under a continuous symmetry. Now I'm going to mathematics a little bit. It may be solved using separation of variable method, that specific coordinate system. Now wave equation and its solution. So if you consider this is the Chial wave equation for the linear medium. And it can be solved in different coordinate system. Three-dimensional coordinate system you have to use to solve this equation. And in rectangular coordinate system, it produces plane collimated beam. As we consider, it will not spread, it will produce a plane collimated beam. In circular coordinate system, it will produce basal beam. I will later explain what is basal beam. And elliptical coordinate system, you will get natural beam. Probably I could not explain it today, maybe next day. And in parabolic coordinate, it will produce parabolic beam, whereas in hyperbolic coordinate system, it will produce hyperbolic beam. Now plane wave. Since plane wave is almost, we everywhere use plane wave, but so long the dimension of plane wave is very small, that is very less than lambda, then and only then it will remain plane, at least to certain extent. Otherwise, the AGFN becomes important. A perfect plane wave or a collimated beam never exists. So if you take a plane wave and it will generate spherical waves, it will generate another plane wave. Then you ask, if a plane wave can produce a plane wave, why not a diffraction-free beam? We can call it. Well, it is, we are considering diffraction, but it still remains plane. What about other beams? Well, the plane wave image plane, we have done it in laboratory. Just think of it. When you are focusing a beam to a pinhole, on the outside, you are getting a spherical wave. From there, you are getting a plane wave. It's something like this. Now, please allow me to go a little bit more. All of you have heard of wavefront and spatial frequency. These two are very important so far as your optics education is concerned. Wavefront and spatial frequency. A plain wavefront, when it comes to length, an ideal length, it produces a ideal spherical wavefront, and it is focused just on the axis, center of the axis, at the origin. And if it inclined a little bit, then it will focus on the same plane, but at different point. Now, one thing is clear, the angle of these rays can be recorded differently on this plane, and this is called spatial frequency plane. So they have different spatial frequencies, and let's go to biprism. What is a biprism? A biprism is a prism like this with very small, these angles are very small. What happens when a plane wave incident on a biprism? So here you will get it producing two spatial frequencies. And because of these two spatial frequencies, you can see straight line changes over the overlapping region after this length. The beam coming out from the biprism has two plane vectors. It has two discrete spatial frequencies. Now I'm going to another term, axial. What is an axial? If biprism is rotated along this axis, the solid just produced is an axis. So this is a solid figure rotating on this axis. And it's same. So this is an axial. What about the pixel frequency of the axial? You can think of a plane wave is coming. Here it is producing. This is the interference pattern here. I will come to that later. It is producing a conical shaped wave. Obviously, this is the spectrum. We can mathematically express this as T rho phi is equal to T to the power I rho by rho naught. This rho naught is the, the radius of this roughly. And obviously it will produce something here. Now output will be like this. If you take Fourier transform of this, it will be like this. So this G naught KR rho is actually Bessel term, and that's why it's called Bessel beam. Beam coming out from the axial as a conical wavefront, spatial frequency contained along a ring. Irradiates distribution, and the output is zeroth order Bessel function, hence called Bessel beam. This is zeroth order Bessel beam. And what about higher order Bessel beam? Let's try to get first to understand what is higher order Bessel beam. I think those who covered Bessel function in your first year class probably, we know that integral representation of Bessel function is like this. And this is zero order. If you add or multiply with e to the power I n phi or plus minus e to the power I, e to the power plus minus I n phi, then it will become higher order. So for mathematically, it's very simple. If you just use e to the power I n phi plus minus e to the power I n phi, Within the integral, it will become higher order decimal function. And in the last slide, I've shown you how to produce a zero order decimal function. But how we can produce a higher order decimal function experimentally, it is really difficult. But before that, let me first explain what is higher order decimal. In fact, it has a direct relationship with helical wave front. And what is the helical wave front? It's something like this. I mean, I hope you understand. It's rotating about an axis. A wave front which is rotating about an axis. And if you just think of a plane, on that plane, from 0 to pi, again from 0 to pi, obviously it has a discontinuity at the center. This is known as helical wave front, and you will see this phase front can be explained as like this. Well, if M is the charge of phase singularity on the beam, which has the phase profile on it. But in the next slide, you will see the meaning of M. Actually, it's rotating, but I cannot draw that here. So if it rotates, the special frequency is also rotating. But it is continuous since it's rotating very fast. Now let me express what is charge. This is M equal to 1. This is M equal to 2. You see, actually, it's two half of the waves are rotating differently. And this is M equal to 2. Obviously, both produce here from 0 to pi, again 0 to pi. 0 to 2 pi, again 0 to 2 pi. So this produces a phase front like this. This phase cross section has X segments, and that M is actually charge of that spherical thing. I mean, spherical thing. There are two waves are in field. It may be, there may be more waves. Like this, it's rotating waves. Is it clear?
Yes, sir, it's clear.
Okay. Unless you respond, I can't follow you. Whether you understand or not. The wave front is like this. That is phase starting from 0 to 2 pi. And actually, these waves are going, one is going a bit faster than the other. Not faster, is lagging or leading the other. The drawn waves. Now, how we can still now we have done the figures and pictures drawn. Now, how we can simplify the simply implement it optically. One is thin annular aperture of radius R1, right between R1 and R2, placed in the back focal plane of the lens, can produce a beam like this. You see, this is a thin annular aperture here. to the all the special because it's lies between 2 pi r1 lambda f and 2 pi r2 lambda f. And it produces the zero order Bessel. But we can produce it using SLN that we have in our laboratory. This is the nature of mask of order. This is Bessel of order 0. This is for Bessel of order 2. We are trying to produce uh, holograms, computer generated holograms. So in case of hologram, you need a reference beam. This is, we are considering a plane reference beam along the axis itself. Reference angle considered to be 0. Now using these Bessel beams, this is the Bessel function generated order 0. This is order 2 and 6 and 20. These are all originated in our laboratory. Now, why we use it? What's the necessity of generating helical waves? Actually, these are very useful for optical tweezers. I think it's better. I will next day I will explain that from optical tweezer. If you have any question, let me tell you one thing. Please go through this article. It's available in net. It's a Feynman lecture. You will get an idea about how the waves propagate. Unless you physically think of it, you cannot think of these type of experiments. Is it clear to you?
Yes, sir.
Okay. So next day I will give my second part. The application of this. Siddhartha, a colony.
No, sir.
So may I close it now?
Yes, sir. If you are comfortable, you can close. So, sir, we have a few questions.
Okay,
Uh,
proceed. Yes, proceed.
yes, sir. The first question is why helical waves are scattering free?
Why helical waves are?
Scattering free.
I'm not saying scattering free. If it can scatters, definitely it will lose its propagation. It is not scattering free. I'm saying it's not scattering free, it's not diffraction free. Only thing is, since it is generated using the concept that it will not propagate. the mass produced, mathematically produced like that, it will not propagate. So it is not propagating. It's propagating, but not diverging. It will concentrate on a small line, small area. Next, I will show you some experimental results, and you will get an idea how it's.
So the
Yes.
next question is, what
So
is the
one
effect
second,
on
Anupam, if may I interrupt? Sir, can you just click on stop presenting so we can see your video clearly?
I can follow you.
So can you just click on stop presenting so we can see your video clearly?
Oh, okay. Right. Is it clear now?
Yes,
sir.
sir. Thank you, sir.
Thank you, sir. So the next question is, what is the effect on plasmonics of helical beam?
Yes. In fact, helical beam, keep one thing in mind, the property of helical beam. Helical beam generated using the concept that it will not diverge. So it can propagate over a small area. So if you want to focus the beam on one point, obviously helical beam is much better than normal waves.
Okay.
Is it
So sir,
clear?
next, yes,
Yes,
I think.
tomorrow I will show you experimental result and then you will get the idea about it.
Okay, sir. The next question is, what will be the spatial frequency of zeroth order Bessel beam at near field?
Spatial frequency of zero order Bessel beam. I show you zero order Bessel beam has spatial frequency on a ring and it is not rotated, it's a fixed ring. You can see it in laboratory. In laboratory, you are in which class?
I am in third year, sir.
Third year.
I'll be
So
promoted.
you have done
I'll be promoted
experiments.
to fourth year.
So you have done experiments. Focusing lasers and
Yeah.
all these six experiments you have done.
Yes.
So you see the spectrum planes,
Yeah.
right? And if a helical beam process using a SLM, if you can generate a helical beam, then you can see the ring. Actually, it's rotating. Zero order is not rotating. Higher orders are rotating. And so if you keep inside that a small microscopic particle, then it will also rotate with that.
So, but the question who has asked, he is asking that he is asking about the spatial frequency at the near field.
Yes. Oh, I've been talking about near field.
Spatial frequency of the zeroth order Bessel beam at the near field.
I understand. That it perfilates something. I mean, ring. In far field, it's ring. In near field, it's deviating from a ring. If you just think of backward, then you'll get an idea about on a conic cone. It remains on a cone.
Okay. So the next question is diffraction limited systems are possible in quantum regime?
I can't follow you.
Is diffraction limited systems are possible in quantum
Quantum,
regime?
actually, if you want to understand it, you have to explain it in quantum regime. It is not possible in classical regime.
So we have, I guess we have one more question, sir. Is it possible to propagate a laser beam without any divergence using this method?
Once more,
Is it possible to propagate a laser beam without any divergence using this method?
actually, you see, as I said, these are all quasi propagation is very less. Absolutely, it's not diverging in normal atmosphere. It contains, whenever we try to do experiment, we have seen it. Even in clean environment, it is always diverting. If you put screens a bit far, then you can see light surrounding. So it's scattering on the dark particles. If you use a clean environment, in fact, my scholar did this experiment in USA. There they used absolutely air-free backbone light, backbone tube. It can go a few kilometers without any.
So
Yeah.
we are done, sir. Or no, I guess there are no more questions.
Thank you very much. So
Thank you,
next
sir.
day I will do the experimental level. Show
Yes,
you.
sir. Sure. We'll be all excited to for the next day talk. And thank you,
Okay.
sir, for your wonderful speech and wonderful seminar and wonderful presentation too.
In fact, it is always better if I can lecture in classroom.
Yes.
Unless I see your faces, it's difficult to go on because I don't know what I am saying.
Yes, sir. But since COVID has put us all in our behind our bars almost, so we can't.
Thank you.
Thank you, sir. Thank you for your valuable time. So I would like to thank all of our speakers for today. And with this, we will come to end of our webinar day one. And I guess,
Just one question.
yes, sir. Sure, sir.
I mean, in classroom lectures,
Yes,
I mean, I don't know whether they are arranging these things or not. Their teacher cannot see all students.
Um,
I mean,
I guess,
in like this, in web lecture,
okay.
if I give web lecture,
Room
carry
for
all
that, where
students.
you can see the participants also.
Is HOD. I'm asking a question. যে তুমি যে ক্লাস নাও ক্লাস লেকচার আমি ছাত্রদের না দেখলে আমার তো আমি ঠিক বুঝতেই পারছি না কি বলছি
Sir is mute.
স্যার
Sir, you are
বলছি
muted.
ওদের বাকি ছাত্ররা তো ইউটিউবে শুনছে, এখানে নেই তো।
আচ্ছা আচ্ছা
ওরা ইউটিউবে শুনছে, এখানে থাকলে দেখতে পেতেন।
আমি তাই বলছি তুই যে ক্লাসগুলো করিস
হ্যাঁ,
তুই ক্লাস করিস করছে তো অনেকে
আপনি যখন প্রেজেন্টেশন দেবেন তখন তো আপনার স্ক্রিনটাই থাকবে না, আপনাকে নিজের মনেই
কালকে জয়দীপ করেছিল যখন আমি একটা দিকে আমাকে দেখছিলাম আর দু তিনজনকে দেখছিলাম আর বাবা সে স্ক্রিনটা দেখছিলাম সেটা করা যায় না
ফুল স্ক্রিন না করলেই হবে, ফুল স্ক্রিন প্রেজেন্টেশন না করলেই হবে,
আচ্ছা
আপনি স্ক্রিনটা ছোট করে রাখবেন।
কালকে তাই করো তো
আর স্যার নাহলে স্যার আমরা পরে একটা অন্য কোনো অ্যাপ দিয়েও ট্রাই করতে পারি, সেটা পরে। বাট কালকে আপনি যেরকম ভাবে বলছেন স্যার ওটা ট্রাই করবো।
ঠিক আছে ঠিক আছে
আর্যমান কিছু বলবে?
হ্যাঁ স্যার, সেটা আমার বলার ছিল যে আমরা যে আজকে ভিডিও অ্যান্ড ওয়েব সিরিজ সব করেছি,
অর্গানাইজড বাই দ্য স্টুডেন্ট চ্যাপ্টার্স অফ ডিপার্টমেন্ট অফ হ্যাঁ, আরিমান কন্টিনিউ কর।
হ্যাঁ সো স্যার সেটা আমি যেটা বলছিলাম যে আমরা যেটা ভিডিও ওয়েবিনার সিরিজ করেছি ভেরি ইনফরমেটিভ অ্যান্ড আমরা অনেক কোয়েশ্চেন্স আমরা নতুন জিনিস জানতে পেরেছি। সো ফ্রম বিহাফ অফ অল অফ স্টুডেন্ট চ্যাপ্টার স্যার আমরা কি এই ভিডিওগুলো আমাদের সাথে ওয়েবিনারটা ভিডিও হিসাবে রাখতে পারি? আপনাদের কোনো আপত্তি হবে না তো?
আমার তো দরকার নেই হেড বললেন বাকিটা
হেড তো নেই।
ও হেড নেই, হেড কোথায়
স্যার
অনলাইনে আছে?
ইউটিউবে আছেন উনি।
স্যার আরসি স্যার ইউটিউবে আছে, স্যার ইউটিউবে আছেন।
ও ও লাইনে জয়েন করেছি।
স্যারের
না,
কাছে লিংক আছে, স্যার চাইলে জয়েন করতে পারেন। তো স্যারের কাছে লিংক আছে।
আমি রাজীবকে পাচ্ছি না, কলিককে পাচ্ছি না। কলিক
টনিকও ইউটিউবে আছে।
কিন্তু কলিক তো আমায় বললো, একটু আগে ফোন করে বললো আমি জয়েন করবো, এই জাস্ট আগে এটা।
তো স্যাররা
হ্যাঁ
যদি দেখছেন
স্যাররা ছিলেন
তো আপনারা
মিটে, দেন
স্যার গুগল
স্যাররা
মিটে
বেরিয়ে
জয়েন
ইউটিউবে
করতে
থ্রু
পারেন।
অ্যাপ্লাই করছে, ইউটিউবে থ্রু ওনার দেখছিলেন, মাঝখানে ওরা ছিলেন।
হ্যাঁ ভিডিও, বাট এখন যদি চান তো আসতে পারেন, জয়েন করতে পারেন, বিকজ এন্ডিংটা যাতে সবার সাথে একসাথে হতে পারে,
আরসি স্যার ইউটিউবে
সবাইকে
লিখেছেন উনি
ending টা
ইউটিউবে
একসাথে
আছেন।
হলে। হ্যাঁ স্যার, কেবি স্যার কি বলছেন?
রিগার্ডিং কপিং, you can copy, I think, do not circulate.
No, so not
Keep it
circulating.
with
We would like
yourself.
to keep it with us.
Yes, yes, no problem.
Thank you, sir.
Um, so with this, we will come to our end of the first day of our webinar. So it was but since we had some of the technical faults initially, but after that it was, I think, a good presentation by all of us. So, and I would like to thank all the participants and all the viewers in the YouTube who waited for this long and was a very good participant. Though we cannot interact, but we're interacting virtually. Still, it was more of a communicative one. So, with this, we'll come to the end of our first day one. There are and tomorrow again we'll be joining the same webinar at 5:30 sharp. So all the viewers are requested to be present tomorrow at YouTube at the same time. And tomorrow we will be having the talks by the second half talk by Sir Ajay Ghosh sir, AG sir, and then the talk by
5:30. My lecture is at 5:30.
Yes, sir.
yes sir.
Okay, okay.
Then there will be talk by Professor Dr. Rajiv Chakraborty and our departmental professor Dr. Puneet Palodi. And so with this, thank you for making this webinar a success. We tried from our end, and we would like to thank SPI, OSA, and OSI for giving us all the necessary permissions and the facilities to organize this webinar.
How many students participated?
So
Sir,
the
the students
highest
are in
viewer
the
were
between,
around
they are asking
45,
questions
and they were concurrent
around
viewers were
45.
around 60.
45.
Total
Very good.
highest 60.
Highest at a point was 45, and total different points accumulated was 60.
It was 60, around 60 total over. So they were a good one. So with this, we'd like to thank all of our presenters. Thank you, sir, for giving us and helping us gain knowledge about different perspectives. So with this, we'll end our webinar day one here. Thank you to everyone, and especially thanks to the student chapter. And thank you. Stay safe, stay healthy, everyone, and good night to everyone. See you tomorrow.
Very
And
much for giving us
Thank you.
obviously,
Good night.
it's a
scope to
pleasure.
let me a lecture like this. This is
It's a
my
pleasure.
first experience.
Thank you. It was wonderful, sir. It was wonderful. Thank you, sir, for being with us for a lot of time together. And thank you,
Okay.
sir. So we'll see you tomorrow again
Thank you,
at
sir.
5:30. Thank you, everyone. Good night to everyone. Stay safe, stay healthy, and hopefully we'll meet tomorrow at 5:30 sharp. And we'd like to not occur any technical faults tomorrow. So thank you
Yes, sir.
for being with us, and bye bye. Good night. Take care.